the webinar. Welcome, Mike. We're ready and very much looking forward to your webinar about salt tectonics in the Southern Gulf of Mexico.
All right, thank you, Clara. And let me know when you see my screen.
Yes, all good.
All right. Well, thank you, everybody, for attending this morning. Probably one of the most exciting things that's happened in the Gulf of Mexico in the last 10 years has been the increasing availability of data from the southern half of the basin. That would be the Mexican half of the basin. There have been a lot of efforts to understand the evolution of the Gulf of Mexico based on what we saw in the northern part of the basin, the US part of the basin. But that was always a little bit complicated because you can't see the autochthonous salt, or can see it at best fairly poorly, in most of the northern Gulf of Mexico basin. So one of the big advantages to being able to work in the south is that there is less salt, there's less allochthonous salt over much of the basin, there's less sediment on top of the salt. So you actually have a chance to see what's going on a little bit. So that's what I'm going to be presenting today, is a look at some broad structural styles in the southern Gulf of Mexico, and then at least our interpretation of what those structural styles mean as far as how the basin opened and what kind of zonation there is in the basin. Before going any further, I do want to acknowledge my co-authors. Ian Norton did the plate restorations that went into this. Tim Dooley, the physical modeling, which is going to be the center of the last part of this talk. And Frank Peel was a good sounding board for a lot of the concepts and discussions that went into making up these ideas. Okay. Page down. All right. To acknowledge the initial ideas that eventually matured into being this talk came at a time that I spent with Pemex back in, wow, probably close to 15 years ago now. And these were the people who participated in that workshop and were involved in some of the brainstorming that had a lot of the preliminary ideas that went into this talk. So thanks to all of them. A huge thanks to both TGS and CGG for providing the seismic data on which the talk is based. And the work was funded by the AGL consortium. And if you want to see who the members are of the consortium, you've got the link there down at the bottom. All right. So broadly speaking, the Gulf of Mexico opened when the Yucatan block, which is colored in blue in this, moved away from essentially the coast of Texas. It used to be snugged up against Texas, and then it pulled back to the south. There were a couple of different stages involved, but pretty much everybody agrees that the Gulf of Mexico opened when this Yucatan block moved southwards and rotated a bit. So you see the original position of the basin at 200 million years in the upper left corner, and then the block started to pull away, and partway through the movement away and the opening of the basin, we had salt deposition, and that's shown in B here in the upper right. And initially, the salt was deposited in one basin, which included the salt both that was going to end up on the US side and on the Mexican side. It was originally one continuous basin. And this salt was deposited partway through basin opening, so that continued opening of the basin actually pulled the Mexican part away from the US part. And that's what's shown down in C, is the present day configuration. And so this was an originally continuous salt basin that was later ripped in half and opened up. Now, most of the salt in the basin ended up on the US side. That would be the northern side. However, Mexico has salt in a couple of different places, and you can see I've labeled them 1, 2, and 3. The southern half of the salt, or southern piece of the salt basin, called the Salina del Istmo Basin, I'm going to be dividing up into two parts, which I'm calling Yucatan and Campeche, and I'll discuss those separately. And then I'm also going to talk about this little area up to the north called the Salina del Bravo, which is the northern salt basin, but it's the part of it that's south of the Texas-Mexico border. So I'm going to be looking at all three of these areas in this talk, and then going to try to use the differences between them to say something about how the basin opened and how this splitting apart or separation of the original salt basin actually worked. Okay. So first, I'm going to be restricting myself to the southern salt basin and look at the differences between the Yucatan piece and the Campeche piece. So again, the Yucatan piece is the part that's up here to the northeast. The Campeche piece is the part that's to the south and southwest. Okay, and just looking at the map of the salt diapirs, you can already start to see some of the differences between these basins. The Campeche piece, just based on the number of diapirs, has a lot more salt in it over a much larger area, and there is much less salt in the Yucatan part of the basin. And it turns out that's not the only difference between the two basins. So I'm going to begin by looking at the characteristics of the Yucatan part of the Salina del Istmo or Southern Salt Basin. So here is a seismic section from TGS showing some of the structures at the Downdip end of the Yucatan salt province. So you can see the base of salt coming down, very smooth dip, and then it comes down dip, and then it goes into a little hole, or actually a pretty fair size hole. It's 2 to 3 kilometers deep. The bottom drops out, the sediments drop in, and that's where most of the salt is. And most of the diapirs are in this hole at the Downdip end of the basin. So from this hole, you actually step up onto oceanic crust. Oceanic crust is what's at the Downdip end of the section. So the Downdip end of this basin is actually 2 to 3 kilometers below oceanic crust, which came as a little bit of a shock the first time I saw it, because what I was taught was that oceanic crust was the deepest part of the basin. And the idea that you actually have something that's deeper than oceanic crust was a little bit of a weird idea. So there's something weird going on here. This is called in the literature the outer trough, the outer marginal trough sometimes. And you have a mirror image of it on the Conjugate Florida margin. So both the Conjugate Florida margin and the Yucatan margin have these outer troughs over large areas in there and stepping up onto oceanic crust. Now, that's not the only difference. The big thing that's going on if you look further up dip in the Yucatan salt province is a huge amount of detached extension. You see these big salt rollers and extensional rollover systems. And this extension appears to be largely Jurassic in age. Now, we're not exactly sure of where the Jurassic-Cretaceous boundary is in here, but it looks like most of the extension going on in here is Jurassic, which is the same era as the salt. So very early in basin history. And if you actually try to make an estimate of how much extension there is, you get areas where it's up to 40 to 60 kilometers of salt-detached extension. So everything's sliding out towards the deep water. Now you have similar structures on the Conjugate Florida margin. They're not as big. Most estimates of extension on the Florida side are sort of in the 15 to 20 kilometer range, but up to 40 to 60 on the Yucatan side. Looking at a more regional view, the previous image I showed was just this box in here, and you can see that the detached extension keeps on going up dip for a considerable distance, all the way to the up dip end of the salt, in fact. So you've got this 40 to 60 kilometers of downslope translation that's generated by this. But if you look for 40 to 60 kilometers of shortening further down dip, you don't see it. Okay, there is not a fold belt with 40 to 60 kilometers of shortening. And this imbalance between the amount of up dip extension and down dip shortening has been noted for at least 20 years. It was first observed on the Florida side, that we just didn't seem to have a compressional province nearly as big as the extensional province. So any model for opening of the basin is going to have to deal with this apparent imbalance between extension, up dip extension, and down dip shortening when it's detached. And the position we've come to, and shared by many others, is that part of this is going to be salt flowing out over newly formed crust. And I'll be talking about this a little bit more as we go along. So that is the Yucatan. And this is the model, a sort of a schematic sketch of the model. So up at the top here, we've got the original salt basin, one continuous salt basin, the Yucatan side on the right, the Florida side on the left, and this little triangle of brown stuff coming up in the middle. That's the mantle coming up. We're just about to have plate separation and start generating oceanic crust. And so the question to ask is, what happens when you take a salt basin and try to split it in half? Well, the best analogy for that is what happens to a swimming pool if you try to split it in half. Well, if there's water in the swimming pool, the water is going to tend to keep flowing towards the middle as you move the two halves apart. You don't get a clean break in the water if you try to rift a swimming pool in half. And we think that's what happened when you tried to rift Florida part of the basin away from the Yucatan part of the basin. And that's what's shown in the lower image here. So you rift the two halves of the basin apart, but the salt flows in toward the middle, at least for a while. And so you can see these two areas labeled outer marginal trough or outer trough in some nomenclature. And the salt was originally further up dip, but it flowed downhill and into these outer marginal troughs as rifting progressed. And we think that is actually what's helping compensate for the extension. So the salt is all flowing down slope to fill the outer marginal troughs, and that's what's giving you this extension. So if you like, the compressional zone is the salt flowing out over newly formed or newly exhumed crust. So the Downdip compressional belt is just the salt flowing seaward onto newly exposed crust. And the key to this is that there's nothing blocking this seaward flow. And you can see up in the title of this slide, I talk about unconfined salt flow. And by unconfined, I mean that there was no buttress at the Downdip end of the basin that was keeping the salt from flowing seaward. So salt is flowing seaward in an unconfined way on both sides, and that's what's giving you this big up-dip extension and down-dip seaward flow. So that's our model for the opening of the Gulf of Mexico basin as observed in the Yucatan and Conjugate Florida margins. Okay, so that's Yucatan. So now let's move to Campeche, down further to the south in the Bay of Campeche. And if you start looking at the crustal structure there, you'll see it's completely different. It looks like you're in a totally different salt basin. So once again, you've got the base of salt, which is the top of the green colored unit. Base of salt's coming down, down, down. You see salt structures coming up. This is again data from TGS. And when you hit the down dip end of the basin, you actually step down 2 to 3 kilometers onto oceanic crust. And there is no outer marginal trough in this part of the basin, or very scarce outer marginal troughs. In most places, this is what you see, is that you're stepping down into the basin. So, okay, that's different. The whole basin is shallower, at least with respect to where oceanic crust is. You're stepping down, and furthermore, no significant amount of salt actually flows down this slope and onto the oceanic crust. You may have just a little bit here. You can argue about what some of these bumps are. But by and large, most of the salt actually stayed put up here. And it's really rather curious that we didn't, if we had this big hole for it to flow down into, it's actually kind of curious that we didn't get salt flowing downhill into it. So a couple of differences here, the big step down and the fact that we don't seem to see much seaward flow of salt onto this oceanic crust. So those are both differences between Campeche and Yucatan. Now let's look at the up-dip end of the basin. So this is where in Yucatan, this is where we had the 40 to 60 kilometers of detached extension in the Jurassic. Well, the top of the Mesozoic, well, the Mesozoic's pretty thin here, but this is it, this bright stuff down here. And there's essentially no extension at all up here. In fact, the only structures you see are compressional, and they're much younger compression. They're actually Pliocene, Myopliocene in age. But you don't see this big extensional province. All the way along here, you don't see it. So again, the radically different margin. This appears to have been a much more stable sort of margin, that you didn't have this big sort of catastrophic early sliding seaward that you had in Yucatan. So Campeche appears to be a much less mobile sort of margin. You're not seeing the same sort of stretching. Now, one thing you can ask is, okay, well, maybe this is because in Yucatan, which in the part A is the part where it says salt in there, that's the Yucatan part. Maybe because we're more on a strike slip section of the Gulf of Mexico, it's more transform dominated opening. Compared to the more truly extensional opening further to the east, maybe that's the difference. Maybe because this is a transform-dominated margin, maybe there was no big hole of oceanic crust that formed early. In other words, there was no down dip place for all that salt to flow to. So Ian Norton actually constructed diagrams showing the opening of the basin and where the oceanic crust is. And the oceanic crust is shown in these various shades of green. And you can see what it looks like after 2 million years and 4 million years and 6 million years of spreading. But you can see that very early in basin history, looking, for example, at 6 million years in D in the lower right, you can see that there is a continuous band of oceanic crust seaward of the Campeche part of the salt basin. So in other words, even though this is a transform dominated part of the margin, you were still generating lots of oceanic crust from a very early stage of basin opening, so that the hole did exist. The deep hole of oceanic crust did exist. So there was a hole for the salt to flow into. So you're kind of left with the mystery of, well, why didn't it flow into it then? Why did it stay perched up on that platform? Okay. If you look at the conjugate margin to Campeche, which is the Salina del Bravo region, which is what I'm going to be talking about later in this presentation. So this is the part of the Gulf of Mexico that's just south of Texas, the Mexico just south of Texas. And you look at the down dip end of that basin, you see a very interesting structure, which is that the base of salt, and that's the subsalt section shown in this gray color or brown color here, you actually have a pretty significant high, structural high in the base of salt that's actually blocking all of this salt from going any further seaward. And this is a structure called the Baja High. I'll be talking about it more later. But at least on this side of the basin, you actually do have a buttress at the down dip end of the Salina del Bravo region that is keeping the salt from flowing seaward. And that gives sort of a hint, maybe, of what's going on in this part of the Gulf of Mexico and why it's so different. And we present that model here, again, with schematic sections. So this is our interpretation of what's going on in the western part of the Gulf of Mexico, which is Campeche to the right and northeast Mexico and southwest Texas to the left. And the idea is we have this structural buttress in the center of the basin, which is keeping the salt kind of ponded on both sides. So this is the Baja High here. And what we're suggesting is that as the basin rifted in half and separated, which is shown in the lower image, these structural highs, you can see the Baja High indicated to the left, essentially pond the salt and keep it from flowing seaward. So for example, this structural high here on the Campeche side is what kept all the salt from flowing seaward and down into the hole on top of oceanic crust. And so in contrast to the basin further east, and that would be the Yucatan, Florida segment, here we're talking about confined flow. There, we suggest that there is a buttress, or was a buttress, at the down dip end of both halves of the salt basin, which was essentially keeping the salt in place and was presenting this kind of early catastrophic seaward salt flow. So because there is no significant seaward salt flow on either side, we don't have the big up-dip extensional provinces of Jurassic age, either on the Campeche side or, in fact, on the Mexico side, the Salina del Bravo side. So this is a rather static basin in contrast. Now, I said there is or was a buttress. The Baja High is still there. I showed it on seismic data. This high, you can see I've got a question mark. The high on the Campeche side is shown with a question mark. We think it was there because something had to block the salt from actually flowing down onto oceanic crust. And we see the conjugate equivalent on the Baja side, but it's not currently there. If you go look at the seismic, you don't see this high still existing over most of the edge of the basin. And so, so there's a question mark. What happened to it? We postulate, well, maybe it had thermal decay or something. The fact is we don't know. We see what we think are, or we infer that it was there based on the absence of seaward salt flow, but that remains an unanswered question in basin evolution. Okay, so what we've got then is a model in which the eastern and western parts of the Gulf of Mexico opened in with very different styles. You had unconfined flow to the east, Campeche, Florida, with salt flowing seaward that leads to big up-dip extension and kind of major early seaward salt flow. But you had a much more buttressed system in the west with little or no early seaward salt flow because it was blocked by these highs at the down dip end of the basin. So that's our model. Now with that, let's take a more detailed look at the Salina del Bravo region. This is again the part of the Gulf of Mexico that's just south of Texas, or the Gulf of Mexico Salt Basin. So the location where it is shown with the green oval in here, the green ellipse. And it's a fairly unique part of the Gulf of Mexico Basin for a couple of reasons. First of all, there's a sharp corner in the basin. It's in the US part, it's trending more or less east-west, and it makes about a right angle bend and starts going north-south. That's because we're moving into the more transform dominated part of the basin. And as part of that, the salt basin becomes much narrower. The brown line is the up-dip edge of salt. And you can see further to the east in the US, say Louisiana, the basin's very, very wide. It gets much narrower as you come to the south. If it gets much narrower, it becomes much steeper. And it also starts getting close enough to the Pacific that you're starting to perhaps feel the influence of some of Pacific plate tectonics. And in all the blue lines here, we show the laramide structures of tertiary age, compressional structures related to Pacific plate tectonics. So the basin's getting narrower, it's getting steeper, and it's getting closer to where there's some basement shortening going on. So the question is, how did this affect the Salina del Bravo region? Just for nomenclature, I'll show this more in a minute. The Salina del Bravo region, at least in our terminology, is the slope in this area. It refers to the slope area. Further up dip, when you get on shore, this area is called the Burgos Basin. It's geologically one single basin, just for reasons of history. Different parts of it have different names. So the Salina del Bravo is going to be the slope. And that's what's shown here. The blue oval, that's the Salina del Bravo region. The Burgos Basin would be the part that's onshore, and depending who you talk to, maybe also the shelf in here. So you can see, in fact, that the Sigsbee canopy, which you see in the topography, is a much narrower feature than it is when you get around the corner and up into the US part of the basin. So, all right, what do we have in the Salina del Bravo region? So here we've got some images from a 3D survey from CGG, courtesy of them. This shows pretty much the whole Salina del Bravo region with the shelf slope break up to the left and going out off onto the continental rise at the right end of the section. And there are 4 big structural features on this. And it turns out that these 4 big structural features are very linear along the basin. So pretty much any section you take in the Salina del Bravo region is going to show these 4 features. And they have a pretty systematic arrangement. And the 4 features from seaward to landward are first the Baja High. Again, this is this high in the base of salt. It's 1.5 to 2 kilometers high in most places. Then on top of that, partly on top of it and partly up dip of the Baja High, you have the Perdido Fold Belt. So big oligomycene salt-detached compressional system. On top of the Perdido Fold Belt, you have the Sigsbee canopy. Again, much smaller than its US portion. It's not nearly as wide. And then up dip of that, you have a very interesting structure that I'll be talking about more called the Bravo Trough. The Bravo Trough is distinguished by a couple of things. First of all, this Mesozoic, which is the blue, is thin or absent underneath much of the Bravo Trough. As best we can tell, there's no Mesozoic under much of the Bravo Trough, which is curious. Also, there is a lot of compressional deformation inside the Bravo Trough, much of it apparently shale detached. So there's a lot of shale detachment and shortening and folding and thrusting going on in the Bravo Trough. More about that in a bit. Okay, here's another section over the same geology. So first you can see here very nicely the Baja High, and you can see that when you have oceanic crust coming in here, you come up 1 kilometer or 2 over the Baja High, and then you go back down again over the other side. So that's the Baja High. It runs along the whole length of the Salina del Bravo region. On top of and up dip of the Baja High, you have the Perdido Fold Belt. Okay. Notice also that the salt does not make it beyond the Baja High. So the Baja High was kind of the buttress at the down dip end of the salt basin. There is no salt seaward of the Baja High. But on top of and up dip of that, you have the Perdido Fold Belt. And on top of the Perdido Fold Belt, you have the Sigsbee salt canopy. And there is an interesting set of age relationships going on in here, because you look at the age of folding in the Perdido fold belt, and it's Oligomycene. Okay, and if you look at the Perdido fold belt on top of that, you can see places, most notably in the center of this section, where the base of the canopy is folded by the Perdido fold belts very nicely. So that would tell you that the Sigsbee canopy was there first. It's older than the Perdido fold belt and got folded. But then you go to other places, like where it says erosional truncation, and you see that the Perdido fold belt was actually deposited over an erosional unconformity on top of the Perdido folds, which would say that the Perdido folds were there first and they eroded, and then you put in the Sigsbee canopy. So you see mutually cross-cutting relationships in age between the Sigsbee salt canopy and the Perdido fold belt, which means that they are broadly the same age. Parts are older, parts are younger. So both of them started in the Oligocene. The Perdido folds and the emplacement of the Sigsbee canopy both started in the Oligocene. And then up dip of that, you have once again the Bravo trough. Now here you can see that this really high amplitude reflectivity that's characteristic of the Mesozoic. Now it's got carbonate in it, which is why it's so reflective. You see that that's just not present under the Bravo trough. So the Mesozoic does appear to be absent in the Bravo trough. And furthermore, at the down dip end of the Bravo trough, between the Bravo trough and where you do have Mesozoic, you have either a vertical weld, which is shown here, or in places there is still a diapir. Here, in places there is actually a salt connection coming down. Now, if you look at the age of the sediment that's in here, there are some wells drilled into the Bravo trough further to the north. Most of the sediment inside the Bravo trough appears to be Oligocene. So this Oligocene keeps coming up, and it looks like something big happened in the Oligocene in here. And if you look, for example, where this big anticline is that folds the base of the Sigsbee canopy, you can see prior to the Oligocene, everything is pretty much uniform thickness. In other words, there wasn't a whole lot going on prior to the Oligocene in here. Everything was being deposited pretty much layer cake. And then in the Oligocene, kind of all hell breaks loose. And so the question that we're going to be addressing here is what happened in the Oligocene to make this formerly stable buttressed margin into something that's so active? Okay. Here is another example I want to focus particularly on the Bravo trough here, where you can see the relationship of the Mesozoic. So up dip of the Bravo trough, at the left edge of this section, you actually can see the Mesozoic. Really nice, reflective, looks just like it does further seaward. And then as you go to the right, it actually dives down and thins and goes to nothing. And you can see the Oligocene section above it expand dramatically as you go into the Bravo trough. So once again, Bravo trough appears to be largely Oligocene in age. Perdido fold belt started in the Oligocene. Sigsbee salt canopy started to be emplaced in the Oligocene. Okay. So this geometry of the Mesozoic thinning to nothing and then huge expansion above it, this looks like what's called a bucket mini basin. And the idea of a bucket mini basin is that what we suggest is that there was originally a diapir here that collapsed. So the reason the Mesozoic is absent is because this area was occupied by a salt diapir, and you're seeing the Mesozoic thinning onto this salt diapir. And this salt diapir later evacuated out and up this weld and into the Sigsbee canopy. So that's our model for the formation of the Bravo trough, which is during the Oligocene, a formerly existing diapir, which we call the Bravo diapir, used to occupy the space where the Bravo trough is now. You loaded it, it evacuated out, up dip, and into the Sigsbee salt canopy. So that's going to be our model. So if you look at how these are all distributed in map view, okay? So here's the Baja High. It's this yellow polygon. You can see that as promised, it runs the whole length of the Salina del Bravo region. The black lines are the Perdido folds. Okay, and you can see that they are partly on top of the Baja High and partly up dip of the Baja High, and they're very linear and extend the whole length of the basin. And then here's the Bravo trough shown in purple sort of color. And actually this funny jaggedy gray line, those are the outlines of the Sigsbee canopy. So you can see that these are all very linear structures. And they run the whole length of the Salina del Bravo. And so it doesn't really matter too much where you take a section across this, it looks about the same. Now, one interesting thing about the Bravo Trough is that I had suggested that it's a salt diapier that's now collapsed. And if it was a salt diapier, this salt diapier was about 400 kilometers long and, well, we're not sure how wide, many tens of kilometers wide, maybe up to 100 kilometers wide, which would make it one of the biggest salt diapiers ever observed, if not the biggest. And so I'd kind of like to be able to say that this is actually a composite of multiple diapiers that's making this. Although when you look at a section through it, and I'm going to be showing shortly a north-south section down the guts of the Bravo Trough, you can't see any kind of segmentation. So at the moment, the best we can say is that this looks like it was just a really huge salt structure. I don't like the fact that it's that huge, but I have a hard time making it anything else. So here is, as advertised, this north-south section down the guts of the Bravo Trough, north to the left, south to the right. If you look at the scale bar, that's 50 kilometers. So you're looking at something roughly 300 and 350 kilometers long. So first off, note that the Mesozoic is absent. Okay, you get a few little bright reflections in places, which may be some super thin Mesozoic here. But the rest of it is all of this Oligocene and Oligomycene gich. There may be some Eocene at the bottom of it. So it's all this young stuff with lots of shale detached deformation. And it also appears to be shingled with the oldest section, the fill appears to be shingled with the oldest section to the north where it's labeled 1, then the younger section labeled 2 further south, and even younger 3 even further south. So either sediments were prograding from north to south down the axis of the basin, or possibly you had different river systems coming from the continent or different sediment transport systems coming from the continent, feeding sequentially from north to south. But the age of the fill is not the same everywhere down the axis of the basin. Okay, so what's going on here? What happened in the Oligocene and the Salina del Bravo? What's our model for this? So let's see what's going on in the area in the Oligocene. So I talked earlier about the fact that we're getting kind of close to Pacific plate tectonics. So you see the area labeled Burgos Basin. That's the up dip end of the salt basin here. Salina del Bravo is further down dip. And all right, we're starting to get kind of close with some of these compressional structures. The black things are the compressional anticlines. They aren't actually getting into the basin, but they're getting pretty close. Now, the thing is, most of this deformation is Cretaceous to Eocene. It's Cretaceous in the west and gets as young as Eocene over here. The age we're interested in is Oligocene. So this stuff's all a little bit old. It's a little bit too far west. And it's a little too old to be directly causing all of this Oligocene stuff that's going on out here. So what else is going on? And you can see actually the first indications of the laramide deformation coming in. You have some big sediment systems of Eocene age coming into the Burgos Basin at the up-dip part of this system. These big sediment transport systems are Eocene in age. So again, a little bit too old to be directly causative to what we're seeing going on in the Oligocene. Well, the other thing that's going on in here is that there is considerable seaward tilting of the basin, and this just shows the age of the outcrops in the Burgos Basin. The oldest outcrops, Paleocene, are in the western part of the Burgos, and then it goes Eocene, Oligocene, Miocene as you move to the east across the basin. So the basin was tilted, and it looks like the up-dip part of the basin was uplifted. So it looks like there is seaward tilt of the whole margin. And so the question is, what is the age of this uplift? When did the basin tilt seaward? Well, that's been addressed in a paper. This is an older paper by Gary Gray. He's got a younger one out. They've looked at this with various dating mechanisms to try to date the uplift of the hinterland in here. When did the onshore part of Mexico start rising? And you see a burial history plot. And different parts of the burial history plot are constrained by potassium argon bentonite, fluid inclusion work, and apatite fission track. But you consistently sort of get an age of the beginning of uplift between about 30 and 35 million years ago, which is Oligocene. And at least in this one place, you've got 5 or 6 kilometers of uplift since the Oligocene. So Oligocene, sort of the red light goes on because it looks like the uplift and tilting of the basin started in the Oligocene, and that's the age that we're interested in. That's the age when everything goes bananas further offshore. So maybe this all has something to do with the uplift, because that seems like it's the structure that's the right age for causing all of this stuff. So you see the effects of this seaward tilting and of the sediment being supplied by the compressional structures further to the west. You can see this in the cluster of normal fault systems that you see in the updip part of the basin onshore and in the shallow offshore. These extensional fault systems are actually Paleocene to the far west of the basin, but then they go Oligocene, and most of the ones near the coast and offshore are actually Miocene. So a lot of this updip extension that you're seeing here is actually Oligomycene in age. Some of it is older, some of it's Paleocene and Eocene, but most of it is Oligomycene. So it seems like there is a large-scale destabilization of the whole system that starts during tilting. Now, if you look at some of this tilting, and the extensional fault systems, you can see that they're actually not detached on salt, interestingly enough. On this seismic section, you see down where it says evaporites, the normal faults are actually detaching at the top of the Mesozoic on something called the Mendez Shale, okay? Not on the evaporites, at least in the onshore part of this system. So if we are hoping to use this extension to actually create the Perdido fold belt, you know, the translation generated by this extension to create the Perdido fold belt, somewhere this detachment is going to have to ramp down on the salt, because the Perdido fold belt is actually detached on salt. So this looks like a partial answer to what caused the Perdido fold belt and everything associated with it, but it's not the whole answer, because our detachment's too shallow here on shore. If we're gonna make this all happen, we need to ramp the translation down onto salt. And we think, although this seismic line is not completely definitive, we think we see that happening. So here is the shallower detachment coming along from the left edge of the section. You can see all the normal faults coming down and flattening onto a structure that is above the salt. The salt is down where the top of the green is. And what we suggest is that this detachment surface actually ramps down underneath the Bravo trough, and actually by the down dip end of the Bravo trough, it's down on the salt. So we say the Bravo trough is where this ramp in the detachment level is. You can also see there are a lot of shallower detachments which create a lot of the shortening inside the Bravo trough, but we think the big one actually ramps down and gets on salt and will ultimately drive the Perdido fold belt further seaward. Okay, so what's our model? Our model, again, this is conceptual, is on the top. This is what we think this area looked like at the end of the Mesozoic. We've got a Bravo diapir sitting in the area where the Bravo trough is someday going to be. And then down dip from that, not a whole heck of a lot's going on. The Mesozoic is fairly uniform thickness. We've got very thin Mesozoic over the top of the Bravo diapir, or maybe in fact completely absent on top of the Bravo diapir. And so this margin hasn't done much yet. Remember, this is in dramatic contrast to what's going on further to the east in the Yucatan and Florida, where there was a huge amount of early extension and seaward translation and all this stuff going on. Again, we're in a confined margin here, so not much has happened. And then here we are in the present and looking at the effects of the Oligocene. So what happened? In our model, we have large-scale uplift at the left end of the section, which tilts the whole margin seaward. And this uplift has two consequences, one of which is it tilts and destabilizes the salt detachment and all the sediments above it, making it all, giving it potential energy, making it all want to slide seaward. That's one thing. But also this 5 to 6 kilometers of uplift in the hinterland supplies a whole big bunch of sediment, which is the yellow stuff, which goes flowing out seaward and also helps destabilize the margin. So what we suggest is uplift destabilizes the margin and triggers extension detached on the Mendez Shale that comes seaward. Uplift also supplies a whole bunch of sediment, which loads the Bravo diapir And the Bravo diapier then evacuates up and out and into the Sigsbee canopy. And so the expansion caused by collapse of the diapier is what gives you all the sediments inside the Bravo trough. And then furthermore, the extension coming down detached on the Mendez Shale dives down under the Bravo trough, gets down on the salt detachment, and then causes the Perdido fold belt further seaward. And the Perdido fold belt is buttressed against the Baja High. So that's why the structures you see in the Perdido fold belt are actually either on top of or up dip of the Baja High. So this gives you all of the main structures, the Bravo trough, Perdido fold belt, Sigsbee canopy, and Baja High in the arrangement that we see them in the offshore. And we think that this was all triggered by uplift of the margin. So that's the common trigger, which is why all these structures are the same age. Okay, well, kind of a cool model, but I mean, this is just me with a pencil drawing this. The fact that we can make a model doesn't mean that it's accurate or that it's real or that it makes any physical sense. So then the question is, can we test this model? And that's what we tried to do with some physical modeling that Tim Dooley did. So he set up a physical model, and I'm going to describe here the setup of it. We started with an autochthonous salt layer. Now, one thing to note here is that in this model, the autochthonous salt layer is flat. We did not attempt to reproduce the tilt caused by the uplift of the margins. So this is all going to be driven by sediment loading in this case. So he built a flat autochthonous salt layer, put a flat-lying sediment layer over the top, vacuumed a little bit off in the middle, which is what created this diapier down in stage 2, and that is our Bravo diapier. Then we built up section on top of, Tim, built up section on top of the Bravo diapier. That's going to be our Mesozoic equivalent. And then on top of the Mesozoic, he put another thin salt layer, actually, which we're going to call the Mendez Shale. He wanted to make a slippery detachment. So this purple unit in stage 3 is the Mendez Shale. And then on top of the Mendez Shale, he started prograding sediments. And this is going to be the equivalent of the sediments that came off of the hinterland uplift. So if the model works, what's going to happen is that this sedimentation is going to destabilize everything. We're going to have extensional deformation that detaches on the Mendez Shale, that's translated seaward on the Mendez Shale, ramps down in the area of the Bravo diapier, ramps down onto salt, comes out and makes a Perdido fold belt out here. Right, so that's going to be this extension compression system. Furthermore, when this prograding wedge gets far enough seaward, we're going to be loading this diapier, and the idea is we're going to be subsiding the Bravo trough into this diapier, and the salt that is currently here is actually going to flow up and out and make the Sigsbee canopy on top of all this. Now, that's a lot of things to happen all at once. And truth be told, when we set up this model, we kind of had our fingers crossed because we weren't really sure that we could make everything happen all at once. But let's see what actually did happen. So we're going to be showing two views here. The one on the left is the view from overhead looking down. The one on the right is from on the floor underneath the model, looking up through the clear plastic base of the model at the bottom of the model. So that's the underside view on the right. Just to kind of get you oriented, this blue stuff here, that's our Mendez Shale detachment. We're going to start prograding across it. This area where it says salt wall, that is where the Bravo diapier is. And this is everything seaward. The seaward end of the salt basin is here where the white line is. And so this area that's sort of cross-hatched further out, that is the area of the Baja High. The underside view here is the area where it says salt wall. This is the Bravo diapier, the Mendez Shale detachments on top of everything over here. And this is the area where we're hoping to form the Perdido fold belt. All right, let's start playing the movie. All right, so you're seeing sediments, all the, whoops, didn't mean to do that. You're seeing sediments here. These yellow at the moment, you're going to see the color keep changing. That's because Tim's adding new layers that are going to be prograding across the model. Okay, so this is the prograding sediment wedge. And you'll notice that the prograding sediment wedge has now reached the Bravo diapir and is actually expelling salt from the Bravo diapir out onto the surface of the model. This is our Sigsbee salt canopy. So at least that much is working. Okay, we are sedimenting on top of the Bravo diapir and kicking salt out into a Sigsbee salt canopy. Now, from here, I'm going to ask you to look hard at the underside view to the right. And you can see that we're actually having some shortening out to the right there. You see things are moving and we're actually creating some kind of compressional structure out there. So that's kind of exciting. We're building a Perdido fold belt. And then if we pause again, you'll notice here, this is the area of the Bravo diapir, but you can see here this orange stuff coming down here and through here, and then also here. This is the bottom layer of the Bravo trough that's actually coming down and welding on the base of the diapir. So looking from below, you're actually seeing it. So you're seeing the Bravo trough coming down and welding against the bottom of the diapir. And you can see the weld spreading as more and more sediments sink into the diapir. And if on the left-hand side, you see the Sigsbee canopy is still extruding and flowing out. So that's in map view. So then the question is, what does this look like in cross-section? So in this image, the overhead view shown in the top, this is a picture of the final stage of the model. There is a white line that is going to sweep northward across the model, and that's showing the position of the sections that you're seeing here. So the current section that's exposed is the one at the very south end of the model. So let's start playing the movie. All right, so let's look at what's what. So the blue stuff, the blue and red alternating stuff that you're seeing off to the right, that's our Mesozoic equivalent in here. All these yellows and oranges and whites and reds up here, that is the prograding sediment that came over the top. All right. So looking from the left of the model, you can see there's a couple of little blue triangles just above the Mesozoic. That's our Mendez Shale detachment. And these are some of the extensional structures. These are actually little reactive diapirs. So we have an extensional detachment above the Mendez Shale. You can see the extensional rollovers into them. So this is the stuff we see in the Burgos Basin. So that's working, okay? And then continuing to the right, you can see this Mendez Shale detachment continues. Here's another blue extensional structure. And then we get to this area here where this yellow and orange stuff has sunk all the way down to the bottom of the model. That's the Bravo trough, the former location of the Bravo diapir, right here. So this is our Oligocene Bravo trough sinking all the way down. There is no Mesozoic under the Bravo trough because there was a diapir there. Here at the Downdip end, in this case, there is still a little piece of diapir left. In other places, it may be welded. And then the Sigsbee canopy is actually, this is a weld coming across like this, little bits of salt left. The remains of the Sigsbee canopy are out here. And then seaward of that, this is the Perdido fold belt, folds and thrusts. And at the seaward end, this is the Baja High. So we've got Baja High, Perdido fold belt, Sigsbee canopy on top of that, Bravo trough up dip of that, and the Mendez Shale detachment going up dip from that. So rather to our surprise, this model succeeded in reproducing all of the major features of the Salina del Bravo area in the right place, all triggered by this sedimentation. So we're looking at a case here, and Tim and I were actually kind of scratching our heads in surprise because these models almost never work the first time, especially when they're this complicated, and this one did. So what this doesn't prove that our model is right, that the uplift and sedimentation and tilting and so forth drove everything, but it does say that our model is physically reasonable. Okay, that in fact the sequence of events we're proposing makes sense because we can reproduce them in a physical model. Doesn't mean we're right, but it means we're at least plausible. So we'll continue to go along. You can see that we've still got a Perdido fold belt, we've still got a Bravo trough. All of the structures actually continue along the whole length of the system. Okay, so then on the bottom, we have my conceptual model. In the middle, we have Tim's physical model. which again, we suggest that they have the same things in roughly the same positions, that the physical model is a reasonably good representation of our conceptual model. And on the top, we have our seismic section showing the Baja High right here, Perdido Fold Belt on top of that, Sigsbee Canopy on top of that, Bravo Trough up dip of it. And so what we are proposing is that all three of these, the seismic, the physical model, and the conceptual model are all mutually consistent, okay? That this is all actually making some sense, and that we think we have a reasonable explanation of what went on here. And what we say is going on here is because this is a confined margin, nothing much happened until the Oligocene. In the Oligocene, there was uplift of the continent, which both tipped everything seaward and supplied a huge amount of sediment. Both the tilting and the sediment destabilized the system. And that's what drove the loading of the Bravo diapir, subsidence of the Bravo trough, emplacement of Sigsbee Canopy, and the Perdido Fold Belt. So, in conclusion, we think that the Gulf of Mexico basin is very different in its eastern and western parts. To the east, we had an unconfined margin, and this is, I'm looking at part B here, which shows this. We had an unconfined margin, which means when we opened the basin, all the salt was free to flow seaward, which give you big amounts of up-dip extension and seaward salt flow into an outer marginal trough. To the west, the area of the heavy red line, we think we had a confined margin, which means that there were buttresses at the down dip end of the basin, which means that not much happened early because there was no place seaward for the salt to go. It was blocked by these basement highs. The Baja High on the US-Mexico, the Salina del Bravo side and Texas side, and a high which we postulate was there but is no longer there on the Campeche side, in both cases keeping these basins ponded so that not much happened on either side until you got into the tertiary. So there is an area in the middle, which we didn't really look at here, where I've got the purple question mark in part B, where, well, our preliminary investigation suggests kind of a mix and more complicated list of things going on. But at least the far east and the far west, we think we understand. So with that, I'll be glad to take any questions.
Hi, Mike. Let me just see if I'm appearing here, and I'm gonna read the questions for you. At least the first portion of the questions for you. I think we have a lot of questions, so I'll try to do most of them. So yeah, first of all, thanks for the really amazing talk. It's really interesting. It's really comprehensive also to see the whole. Not the whole, but a very long evolution of the basin from the Jurassic opening to the Oligocene, Paleocene. So it's very, very interesting. So I'm going to start from the questions in the Q&A box. So yeah, the first one is from Joshua Turner. He says, I wonder if any of the Yucatan salt flowed to Florida side before the trough opened.
Yeah, probably. I mean, it's really unlikely that in the early stages when the swimming pool was still rifting and everything was still connected, I'm sure some salt from each side got onto the other side. So it's really unlikely that there was a perfectly clean break and that US salt stayed US and Mexico salt stayed Mexico. So yeah, it seems likely to me that the final break left some salt stranded on the wrong side. I think that's pretty likely.
Yeah, I agree. Actually, that leads me to one of my many questions that I probably don't have time to ask. Do you see any evidence? I mean, I think you probably already said some of that, of seeing the position of salt flow. Maybe some seam rifts driven salt flow in the outer trough.
Yeah. Well, it depends how long salt deposition took. Some of the stuff that Frank Peel's been doing suggests that salt deposition may have been geologically darn near instantaneous, as in 50,000 years instantaneous. So yeah, sure, there may have been a little bit of syn depositional salt flow, but if it really was that fast, syn depositional is such a short time that there may not have been a whole lot of time to do flow. if it's a few tens of thousands of years. So if it was really that fast, then not a lot. If it's 3 million years, then sure, there would have been some.
Okay, yeah, no, that's a good point. All right, so we can move to the next one. So the next one is from Faye Geiger. She says, Mike, can you elaborate some of the reasoning behind interpreting the spreading center as going down the western part of the basin and not interpreting a large western transform?
Sure. The geometry of the spreading center that's shown in C, for example, on the slide that's currently up, is from gravity data. Okay, and it's actually imaged on gravity data. It's really, this is some of the Sandwell and Smith stuff, and it's really spectacular. And I think there's not a huge lot of debate about it. Well, furthermore, we've also got a fair amount of oceanic crust over there. And if it was a pure transform margin, we wouldn't have any oceanic crust. So, we don't know anything, but that seems reasonably well constrained that the geometry of the spreading center in the West is probably like that because it's imaged on the extinct spreading center is actually imaged on gravity data.
Okay, right, thanks. So the next one's from Matt Fab. There is still significant amount of salt on top of the Baja High. Why?
Okay, well, we think that the Baja High was there during salt deposition and that salt lapped onto it. And then the question is, if the salt was thick enough to actually get up on top of the Baja High, then you'd actually have some depositional salt on top of the Baja High. So some of it could be depositional salt on top of the Baja High, especially because we think we're in deep water here. So a lot of the salt that's being deposited is being deposited either at the downdip end of turbidity currents, kind of coming off of the continental margin, salt turbidity currents, or raining in suspension down from above. And in either one of those scenarios, you can actually get a little bit of depositional salt on top of the Baja High. And then furthermore, during the later shortening and seaward translation, you may have some salt carried on top of the Baja High on thrusts. So some of it may be depositional, a little bit may have been gotten there during some of the later seaward translation.
Okay, yeah, that's a very good point as well. Let me see, the next one is from Joshua Turner again. So he has a comment actually. You should consider what velocity error might be doing your deep image. I think he doesn't really refer exactly where. So he says, I think it's less complicated looking reality. I don't know. It's probably
it depends which image and which parts. I think the Baja High is quite real and is not a velocity artifact, in part because in areas the Baja High is actually outboard of the salt. To the north, it's outboard of the salt. So the Baja High is real. Now the rest of the base of salt, a combination of velocity error, poor imaging. Yeah, I'd be very happy to say that my base of salt, when you get further away from the Baja High, further to the west of the Baja High, could very easily be modified. I'm not emotionally attached to that part of the interpretation.
Yes, and he doesn't really refer specifically which section or which portion of the section. It was halfway through the talk, so I imagine it's the key section on the Bravo trough. But yes, I'm with you. I think the Baja High, it's a really confident peak. It's not really that hard to image and to map. Joshua, if you want to then comment later on, I can try to follow up. So the next one's from William Federgay Wilson, sorry. Is there another Faja de Oro further to the north offshore?
Well, I would love to answer that question if I knew what the Faja de Oro was. So I will have to confess my ignorance on that. And if you ask a follow-up question, I'll be glad to answer. Otherwise, I'll just say no. And then,
Yes, me and you both, I don't know what that means. Sorry.
Yeah, so I'm going to have to confess some ignorance on that.
Yes, so Rosanelle
Romero.
Oh,
all right. They just added one in chat that it's the Golden Lane. Yikes. So the Golden Lane is essentially a reef trend, for those of you who don't know, that's in the sort of the Salina del Bravo and actually a little south of the Salina del Bravo region. We think that the margin actually was dipping off towards deep water. So I think there was really only one coastline. So I don't think that there is a whole nother set of reefs. Well, I don't think it's likely, I'll say, at least not in the sense with the Gulf of Mexico full of water. If you want to sort of start playing with water level drawdowns in early parts of the basin, you could probably put one further outboard. But if you go seaward of the Golden Lane, you were getting into progressively deeper water, at least in our reconstructions.
Okay. So the next question is from Rosanelle Romero. She asked, what event has deposited the main shale, and what was the gross deposition environment? And if that could be the reason it was the ideal shallow detachment zone.
All right. Well, I'm going to have to be ignorant on this one too. The age of the Mendez Shale is Maastrichtian, and there are Maastrichtian shales in a lot of places around the world at the time. And I think Mudrock's people could give a much better answer to that than I would. I mean, it was evidently a really good shale, a really slippery shale. And I confess to not knowing the detailed reasons why. So sorry.
Yeah, that's okay. So the next one again from Faye Geiger. How is including the Paleocene-Eocene deposition between Mesozoic and Oligocene of the Wilcox changer model? Why do you think that sediment dump didn't trigger diaperism folding?
Paleocene and deposition, how would it change the model? Well, first of all, the lower part of the Baja Trough may be Eocene. The parts that have been drilled, there's something like 19,000 feet of Oligocene got drilled and they didn't come to the bottom of it in a well near the north end of the trough. So parts of the Wilcox may be down at the bottom of the Bravo Trough. Also note that the shortening in the hinterland was going on during deposition of the Wilcox. And so that may be ultimately the source of a lot of Wilcox sands. So I don't want to say that there was zero sedimentation prior to the tilting in the Oligocene, because clearly the Wilcox is a major reservoir in that part of the basin. But it just looks like the rates, especially in the Salina del Bravo region, the rate of deposition just went through the roof in the Oligocene. So I suspect that the Wilcox is related to the Laramide, but it doesn't look like the tilting started until after Wilcox deposition.
Okay, all right. Yeah, good. So the next one from Scott Kruger. Are you willing to speculate on what may have happened to the missing high in the Campeche?
Yeah, I hate that question because it's the weakest part of our confined basin model. I think we have strong evidence that the salt was confined in Campeche, and it's just really inconvenient for the model that we don't see the buttress that confined it. And so I can make up stuff like, okay, it was it was a volcanic and thermal high, and there was later thermal subsidence which caused it to decay. So sure, I can make up scenarios, but that's different than actually having a real model with evidence. So my argument is we think there was one based on the fact that salt did not flow seaward, and it's not there now. Those are the two things I'm reasonably confident about, and everything else is just a guess. So, I mean, truth is, I don't know.
Yeah, no, it's a tough question. I agree.
Yeah.
I was actually, when I was looking at that model, I was wondering, could it be that the Baja high was there? It was just one high and then was rifted apart from the other side. So it remained in the western.
Yeah, the problem is I showed that thing about the creation of the oceanic crust very early in the basin, that, after 6 million years, the basins were completely separated. And so I need to keep the high on the Campeche side there longer than that. So yeah, I considered that and couldn't make that work either. So yeah.
Right. I try. It was worth an effort. Okay, I think, I'm gonna ask a couple more questions, and then Clara, I think she will carry on with the rest of the questions. I just want to ask if it's okay for you to.
Yeah, I can stay for another 10 or 15 minutes if we need to.
All right, brilliant. So the next question from Byron Veilleux. In all the continental margins where spreading stances have developed, have you observed any similar features to the Baja High that might match this early thermal uplift?
Well, I mean, one of the possible explanations for the Baja High is that it's a continental fragment, and that those are observed in a number of places. It could also be some kind of a volcanic edifice. Those are observed, a volcanic plateau of some sort. Those are also observed. So depending what you think it is, yes, there are structures that could be analogous, but until we actually know what it is, we're just kind of waving our arms in the air. It's clear that it's there on the Salina del Bravo side. It's definitely there. And there are outer highs on a number of other margins with a variety of different origins, continental fragments and volcanic plateaus being the two most common.
Yeah, all right. Good. So the next one from Ioannis Alexandridis. What do you think is the physical mechanism which choose the shales instead of the salts for the detachment?
Okay.
Is it a matter of rock strength or something else?
So it could be a couple of things. There are no salt diapirs up in the Burgos Basin in the onshore. So we're not entirely sure of the composition of the evaporites there. Given that it's the up-dip part of the basin, it's possible that they were more anhydrite dominated than the more halite-rich parts further down dip. So it could be a rock strength thing, or it could also be just a rock mechanics thing. And if you've got two very weak detachments and you start prograding across, it's going to detach on whichever one is least work. And so it may be that that the men, if they were both of comparable strength, it may be that the shallower one just made more sense from a work point of view. You know, less mechanical work involved in doing them. It could also be that the salt is thin up in Burgos Basin. The evaporites are thin. And it could also be that any small basement steps actually disrupted the detachment layer so that it was not a favorable surface for regional translation. So any of those could be. I don't know which one it was.
Probably a combination of the three.
Yeah, it could very easily be a combination. I mean, the easiest one is just saying, hey, it's a lot of anhydrite. But
yeah.
But I don't know.
I mean, all those three hypotheses make sense. So yeah, could be as well be two or three of them. All right, Mike, I'm actually gonna have to leave the question and answer session. I want to thank you again for the amazing talk. It was really, really interesting. And I'm gonna pass to Clara. Clara, I think will join now. Okay. Bye, Mike. Bye.
All right. Bye-bye. Thanks for your help.
Hola. Thank you, Leo.
Hey, Clara.
Hi, Mike. That was great. I enjoyed it very much. We do have many more questions, so you said you can stay a bit longer. I see an earlier discussion in the chat. Bruce Samuel, he asked, could the apparent absence of Mesozoic sediments in the Bravo Trough just be the absence of carbonate deposition?
Sure, it could. There are two arguments against that. One is that you have Mesozoic both up dip and down dip deposited, so why there would be a gap just in a linear fashion along the margin there. And the other one is, let me go back, showing the seismic. Up there. So the big problem is this huge expansion that you see of the younger section in the Bravo Trough. And thinning of the Mesozoic and the stuff that's above, like the Paleocene and Eocene, they all thin coming down. So this Oligocene Gich pile can get really thick. And so what was moving out of the way in the Bravo Trough to allow this huge expansion by a factor of like 5 of the Oligocene section into the Bravo Trough? And it's the expansion into the trough, which seems to be most consistent with the idea of a diapir, along with the fact that there's this weld at the down dip end that feeds a salt sheet. So all of those things seem to argue together that there was actually a big diapir in the area. So that's the root of our argument anyway, rather than just being some kind of a depositional thing.
Thank you, Mike. There is a comment regarding that from Mark Rowan. He says, is the apparent lack of Mesozoic due to the image? Other 3D data show imbricated Mesozoic in at least the southern part of the Bravo Trough.
Yeah. Well, this particular line seems to show the Mesozoic thinning reasonably convincingly with a good image coming down in. I don't want to say that there's no Mesozoic anywhere in the Bravo Trough, mostly because I hate the size of a diapir that's that big. And I've actually seen places where it looks like you have some locally thick Mesozoic in there that may have been actually Mesozoic mini basins on top of the diapir, which were later pushed down to the bottom. So I don't want to pound the table and say that there is no Mesozoic anywhere, because anytime you say something like that, you're always wrong. I would say Mesozoic is missing over most of the area. And I would look forward to seeing more detailed work as to what is and isn't there underneath the Bravo Trough. So I don't want to, I'm confident it's missing over much of it. I certainly don't want to say it's missing over all of it.
Okay, thank you, Mike. I'll continue in the chat for earlier messages. Andrew Pepper, he made a comment, your Oligocene events fits well with our model of the exhumation of the Permian Basin, which we place from 35 million years to present.
Yeah, in fact, this uplift of the continent continues all the way across the southern United States. If you just look at a geologic map of the United States, you can see this pattern of progressively older units at the surface further inboard. And that's been dated as Oligocene in a wide range of places, the Permian Basin being one, but you can track that all the way over into Louisiana, Mississippi. So it's actually a really regional event. And, and arguments about pieces of plates passing under the US and so forth. There's a lot of discussion of what it might be, but it's a pretty well-known regional phenomenon. So we're not making it up.
Great, thank you. We have a question from Tiago Alves. Are you okay when comparing the size of the Bravo Trough with the volume of salt in the 6B salt canopy and below? Would you expect the canopy to be slightly larger, or would have you lost a large volume of salt due to dissolution in addition to the tectonic tilting you observe? Any thoughts?
Yeah, so here's the thing. So if you look for other feeders underneath the 6B canopy in this area, okay, there's a feeder at the up dip end where the Bravo Trough is. I mean, there's still salt in it in some places, in other places it's a pretty clear weld. So a lot of salt came out of the Bravo Trough into the 6B canopy. If you look for other feeders, there are very few decent examples. And most of the ones people have proposed is, oh, I've got an area of bad data, I'll throw a feeder in there. So it does look like most of the salt in the 6B canopy did come out of the Bravo Trough. Now, what I don't know, I've never tried to do a volume calculation of it, okay? I mean, the Bravo Trough's really big. I mean, so it could, at least qualitatively, it looks like it could supply the amount of salt we see up in the 6B canopy, but I've never actually tried to do the volumetric calculations and make it work.
Thank you, Mike. There is a comment from Gopal Amruthapuri. As always, great work and great presentation, Mike. From Shashran Sherkati. Hi, Mike. Thanks for excellent and insightful presentation. I have a question regarding presence of sand with Eocene age in Perdido Fault Belt, considering presence of Bravo Salt Dome. Thanks.
As a barrier, yeah. So it's entirely possible, well, two answers to that. First off, it's entirely possible that the salt wall was not a continuous barrier and that there may have been channel or sediment transport systems that crossed it in places. Okay, it doesn't necessarily mean it was a structural high for 400 kilometers long. So it may have had a little bit more complicated topography than that, and there may have been places that sediments could breach it. Also, especially if you're talking about the northern end of the Perdido Fold Belt, it's entirely possible that sediments could be coming around the north end of the system. So I think some sediment probably was getting across the structure, and some of it may have been coming from the north as well.
Okay, sounds reasonable. Mike, are you okay to continue so we can jump into the Q&A now? Or
yeah, I can go for about another 5 minutes, I think. Okay,
good. So I'm now going to the Q&A question from Team Grow. Oligocene uplift correlates with a splitting of Farallon plate into Cocos Nazca plate, formation of Trans-Mexican volcanic belt, and uplift due to flat slab subduction. This occurs in southern Mexico. Do you think this is the cause of the uplift in the Burgos Basin?
So to answer that question, again, I'll refer to the fact that this seaward tilting and continental uplift goes all the way across the southern United States. And it's not all exactly the same age everywhere. And so arguments for this include some of the stuff he's talking about. Also, subduction of a spreading ridge, flat slab subduction, pieces of subducted plates breaking off and sinking down into the mantle. Almost everybody agrees that with the scale that we're seeing here of thousands of kilometers in lateral extent, that you've got to be talking about some kind of mantle phenomenon, probably related to the geometry of the subduction at the western edge of the system on the Pacific margin. I haven't seen something that would give a single cause, a single simple cause for the uplift all the way from southern Mexico through northern Mexico through most of the southern United States. It's likely that any subduction and breaking up of things into subplates is not going to cover that entire region. It may be more localized in southern Mexico or northern Mexico or Louisiana, for example. It's certainly mantle related and probably Pacific plate related. I think the jury may still be out a little bit on exactly what aspects of this are causing it, because the uplift is just enormous in terms of its areal extent.
Okay, thank you, Mike. We have 2 more minutes, so I'll make another question from Stephen Schotter. Do you have any idea how much influence the Oligo-Miocene igneous activity has had on the development of structures? West Texas SMO volcanism is of that age, and there is a scattered activity in northeast Mexico extending east even to the Mississippi Delta at that time.
So the Oligo-Miocene uplift, it seems to be like it's post-orogenic uplift with respect to the laramide. Okay, so the origin of that volcanism is probably tied into that larger relaxation of shortening. There are a variety of models for how the volcanism happened. I'm not aware of a direct link of the volcanism to what we're seeing here, other than that it's going to affect the mineralogy of the sediments that we're seeing in the area. But I think they are likely all responding to the same set of much larger geodynamic events. The end of laramide shortening, the stuff going on in the mantle with Pacific plates passing and breaking and doing all these things, they're probably all tied into the same series. So they share a common cause. But otherwise, I haven't come up with any clear direct link between them, other than they're probably caused by the same set of events.
Thank you, Mike. So it's almost 3:20 now. We do have many more questions that we can email you. If you
tell you what, I mean, there's still 135 people on, so I'll stay another 10 minutes if
perfect.
Get through the questions.
Okay, great. Yeah, so we have another from William Fethergill Wilson. The Gulf of Mexico partially dried up during the formation of the Yucatan Channel.
What's the age of the Yucatan Channel?
Okay, William, if you can clarify.
Yeah, I don't know. If this is talking about the like the Eocene or Oligocene drawdown, well, the drawdown for the Wilcox, I'm not a believer in that. But if you're talking about earlier, we can, like in the Jurassic, we can talk about it.
Sounds good. So we have Douglas Heller asking, Mike, how does the Chicxulub impact relate to your model and timing?
Well, 2 levels of answer. The most direct one is in terms of the deformation that we're seeing, say, in either of these places, it doesn't. I don't think that the impact triggered the deformation that we're seeing here. Now, more regionally, the Chicxulub impact really marks the change, or even may cause the change between the carbonate-dominated Mesozoic and the more clastic-dominated stuff that we see later. So it's certainly of huge importance in the overall history of the basin. But in terms of the detailed events we're talking about here, the timing's wrong. I mean, Oligocene is our big time in the Salina del Bravo and Chicxulub's Cretaceous Tertiary boundary. So I don't see any direct link.
Okay, thank you, Mike. Ted Goto, hi Ted. Why did the Baja High form? What tectonic forces existed pre-salt time to elevate the high?
Okay, I've mentioned that in passing in some earlier questions. The most straightforward models for what the Baja High is are that it's either a continental fragment rifted off or that it is some kind of volcanic edifice. And either of those can and do occur during rifting and plate separation. I don't think it's a compressional feature like a fold. Okay, I agree with Ted that I don't see a compressional force to make it in terms of the deformational structure. But I think if it's, I think the reason it's high is because it's either a volcanic edifice or it's something lighter like a continental fragment. I think those are the most likely ones. I'm looking forward to when people get into some serious potential fields work or something and actually start coming up with models of what the Baja High might be.
Okay, yeah, sounds great. I'm jumping to the chat now, just seeing the time of the questions. From Antonello Simonetti, could the Campeche margin have had a more gentle gradient compared to the northern side, which could have inhibited salt flow and up-dip extension? This basin asymmetry would not imply the presence of a Baja High equivalent to the south, which could explain why we do not see it on seismic. Just a thought. Great presentation.
Let me find the, nope. There we go. No, that's not it. That'd be where I talk about confined versus unconfined. Can't remember where in the presentation that is. Ah, there. Yeah, so if you want to change this part A and basically make the Campeche side flat instead of having a little lip on the end of it, those are some games you could play. I mean, the salt is thinning towards the edge of the Campeche salt basin, so I think the basin has to come up at least a little bit. But you can certainly change the shape of what I drew there and make it less dramatic. Yeah.
Okay. Thank you, Mike. Sevolod Egorov is asking, how do you define crustal type boundaries? They're not obvious from seismic, so your marginal highs could be within either oceanic or transitional continental domains?
Well, that's correct. Again, I have no idea what the Baja High is. And if it's some kind of volcanic edifice, then you could sort of make a case that we're talking about some kind of volcanic crust. I also, just in case anybody's wondering, I don't think the boundary between oceanic crust and transitional crust is a jaggedy line. Yeah, there's a reason I didn't add any detail to my big gray areas and purple areas in here is because I just don't know what's going on. So yeah, the crustal boundaries, you can mess with them. Now, at least on the southern Gulf of Mexico side, the magnetic data is pretty good as to where the limit of oceanic crust is. The northern side is much less certain based on potential fields. But the southern side, I think we actually do have a pretty good idea where the limit of oceanic crust is.
We do have a comment from Tim Grow regarding the Baja High. He says, Baja High may be transpressional ridge, much like that found along Romanche Transform offshore Ghana, classic shear margin structure.
It could be, except everything that we know about this and the fact that you're generating seafloor spreading is this appears to be a transtensional ridge. Now, you know, you can play games with little segments that are misoriented with respect to other segments, but I'm leery of transpressional explanations in what is overall a transtensional margin. So, you know, I think there's a lot of work to be done on what the Baja High is. And I think, but if I stated an opinion on it, I think it's X, I would almost certainly be wrong. So I try to stay out of that one.
Thank you, Mike. Another question from Sevolod Egorov. Outer edge of the Campeche province, last slide, coincides with free air gravity high, which can be traced all the way to the northeast. Could it be form COB marginal high, which actually present everywhere along the Mexican Campeche Yucatan margin?
Could it be composed of what? What was the last sentence?
From the COB marginal high, so continental ocean boundary marginal high.
Well, I mean, I am proposing that it is a COB marginal high because it's at the COB and it's a high. Now, the free air gravity, you know, let's not all go down that road. On seismic, it does not appear to be a structural high at this time. Now, based on the seismic I've seen, although that's going to be subject to the velocity models. I'd be happy, I'd be overjoyed if somebody could come up with an explanation of why it's there and could convince me that it's somehow still there and that my early efforts to see it were somehow misguided. I've been driven mostly by the seismic, where looking for it, I just couldn't convince myself that there was a believable structural high in the base of salt there. I'd love it if there were, because it would simplify my explanations a lot.
Thank you, Mike. We have a bit more time. Do we have any example of the Baja high in the South Atlantic margin?
It's a variant of questions that we've talked about before. I mean, there are lots of places. There are volcanic plateaus, certainly in the South Atlantic margin, pretty far outboard. So if it's a volcanic plateau, then yes. Continental fragments, most of the ones I'm aware of are actually in the North Atlantic. But it's not my area of expertise, the basement structure of margins. So I think there are probably other people in the audience who know more about answering that question than I do.
Good. Yeah, that was from Mohammed Abdel Fattah. Another question from Sevolov Egorov. There are models that at least Western Gulf of Mexico formed largely mechanical extensions of the crust. If so, could be the Baja is a core complex structure formed by a low angle detachment fault and be analog to the structure of the Galicia margin?
Yeah, that's another one. There's all the stuff that goes on about non-volcanic margins. Although if you start talking about the Gulf of Mexico as being volcanic versus non-volcanic, you'll probably get in a fist fight pretty quickly, because I think it's different things in different places. A core complex is another possible explanation, although it's a little, in my impression, it's a little bit short wavelength and steep sided to be that, or it's at least steeper sided than core complexes I've seen in things like the Galicia margin. But yeah, that's another explanation, sure.
Okay, so there are comments also from, we have one from Scott Kruger. Mike, great work. I like your model, and not just because it fits with cryptic models I have developed back when I worked in the Gulf of Mexico. I'll give some thoughts to the missing high and maybe send you an email to follow up. Thank you.
I would appreciate it. If I had I think the model would be more convincing and certainly easier to present if I had a convincing explanation for the missing high.
Yeah, so excellent work, Dr. Hudec from David Maldonado. Very interesting talk. Thank you. I have been looking forward to this after reading Dr. Hudec's paper. That was from Rosanelle Romero. Thank you for the new technical term, Oligocene. Oh, I cannot pronounce that. Oh,
the Oligocene Yich pile. Yes.
That way, yeah. That was from Faye Geiger. Excellent presentation from Mohammed Armal. So many people happy about the presentation. So it's 3:30 here in the UK. So for you, it's 9:30, I think. We will let you go. We're very grateful for having you to present, the first webinar of the third season of the Salt Basins Technical Interest Group. Thank you everyone for connecting. It was a record of 260 people connected to listen to Mike today. So thank you so much for supporting us. And well, I can email you the rest of the questions. So
okay,
maybe,
thanks, Clara.
Yeah. Okay.
And thank you all for attending and hanging in there during all the Q&A.
Yeah, still 100 people connected. Thank you so much, everybody, and see you in 2 weeks.
Right.
I think we'll have Angola, so West Africa talk. Thank you.
All right. Bye-bye.
Thank you. Bye.
Bye. Bye, Clara.